Welcome everyone. Welcome to FIFA Gameplay Automated Testing with Jenkins. My name is Stuart Rowe. I'm a software engineer at Electronic Arts, and I work on the FIFA Gameplay team. So my talk is going to focus on how we improved our existing pre-flight testing system by moving to Jenkins. And when I talk about improving, we're focused on increasing our test throughput, creating a system that we can maintain so we can use it in future development cycles, as well as create a system that our engineers actually wanted to use, that they found intuitive, and they could adopt it into their daily workflow. A little bit of background on what FIFA uses our pre-flight test system for. It's used during our filing period of development when we want to verify bug fixes going into our game to make sure that those bug fixes aren't having any unexpected knock-ons on performance or stability. So we take a pending change, we're using Perforce, so these changes are packed into change list shelves. And we run that change against our entire test suite, which includes automated smoke tests, profiling memory collection tests. We have some functional gameplay tests, and we take the results of those tests and compare them against a daily baseline that was created earlier in the day. And from that difference, we can see what impact that change has. And by using the system, we're able to increase our confidence in every change that goes into our game. So our previous system was implemented as a set of bash scripts that coordinated calling our existing build and test tools. And because of this, we had no ability to parallelize or scale. We ran on one machine, and we had one test running at one time, and it was about a 3-hour turnaround period. We couldn't tell our engineers how far through the pipeline their tests were, and we had to collect results manually into emails and send that out after the test completed, so it was a big manual job. So we turned to Jenkins because it provided scheduling tests in parallel. It allowed us to create scalable build pipelines where we could add more machines to a build farm and get more test throughput. We could automate reporting, we get emails being sent out automatically, and we could visualize our build pipelines through the Build Graph View plugin. And through the web UI, there's a very accessible interface that our engineers could use and felt comfortable using on a daily basis. So in moving to Jenkins, we found there are a number of challenges, but the most two interesting challenges I'm going to talk about today are how we approached archiving our builds and how we created our build pipelines. So in my experience with Jenkins, there is a typical workflow pattern for archiving builds where a build project produces some build output. That build output is artifacted and archived on the master server. And then later, when a test project needs to consume that build output to run a test against the build, it copies that artifact from the master into its own local workspace, and then runs the test. The problem for FIFA is that our builds are quite big. They're on the order of 10 to 20 gigabytes each. And our big concern was how this copying directly to one server was going to affect our overall build and test times, as well as looking forward to scaling up our build farm. What's going to happen to the server bandwidth as we have more build machines all pushing their builds to one central server. So the solution we came up with was to have each build machine own its own build archives. And then we only copy one small artifact file to the master, which facilitates that build sharing. The implementation details of this are we have each build machine configured with its own local build share. That's a network share that it knows about. As the build project completes, its final step is to copy that build from its working space to that network share, and then generate a property file that describes the parameters of the build as well as where it actually stored that build. And then the test jobs would come along and copy that artifact that contains the network share and parse that, and then know where to copy that build from, and we copy directly between our build machines, avoiding any large hit on the server. The second thing I want to talk about is how we approached creating pipelines like this. This is the typical example of how we try to approach pipelines. So on the left side, there is a build phase where we're going to be generating builds for a set of configurations. In the middle is our testing phase where we're going to take those built configurations and we're going to test each one against some set of test types. And then finally, we're going to collect all the information about the build and test phase, and we're going to create a report that's going to encapsulate what actually happened. So our build pipelines rely extensively on the build flow plugin for orchestration. And in the previous slide, I showed build phases and test phases, and we describe each of those phases as a collection of closures that are going to execute the necessary jobs. Each of those jobs is going to be one of our fundamental build steps, such as building code, building data, running a given test, and submitting changes. And we can identify jobs that ran by assigning each job a unique key, so that a test phase job that needs to refer to a build can look up that build from the previous phase. And then we take all these build pipelines, all the information about the jobs that ran in each phase, and we can serialize that into JSON, and that JSON can be used to easily create reports from. So I have a brief code example. It's a pseudocode example, so it's not going to actually work, but it's going to show you how we approach this problem and how we track everything. So assume we've created this argument map that's going to contain all the build configs that we want to run, and we've generated that build config list from our build parameters as well as other external sources. So we're going to iterate over each config, and we're going to call this helper method that's going to generate a closure for us. So for that current config, we're going to be setting up a parameter map, and we're actually going to use the build flow build method to schedule the build on the target project. We're going to push that closure into a map, and that particular closure is going to be identified by a unique build key that's going to depend on the current configuration. And after we've collected all our closures into our build closure map, we can then run them all in parallel using the build flow parallel method. When that completes execution, it's going to return a map object, which I've called a join because it's waiting on all the closures to complete. And that map is going to have the exact same key set as the build closure map that we passed into parallel originally. And the value set are going to be a collection of flow run objects, which encapsulate the actual jobs that ran. Similarly, we're going to iterate over a set of tests for our test phase. For each test type, there's going to be a particular config we want to run, or a set of configs we want to run for that test type. And then we can use that same build key helper method to look up the build from the build phase in the build join map. And we're going to pass that into our helper method for generating a test closure, so we can look up the build number to facilitate artifact copying. Then we're going to run our test in parallel. If anything fails during the build or test phases, we include that in a guard section provided by the Flow DSL, which works just like a try-catch block. So if any of our builds fail, we're going to assume that we don't want to continue testing, and we're going to jump down to our rescue block, where we can generate a report still to show which build step failed. And this also acts like a filing block where we can execute after, even if both the build and test phases complete successfully. And then finally, we can use our build join and our test join that collect all the information about the jobs that ran in those earlier phases to generate a report from. So how successful were we in moving to Jenkins? For FIFA 15, compared to FIFA 14, we were able to evaluate 500 changes, so 500 bug fixes we wanted to commit to our game to ship, versus 200 in FIFA 14. Of those changes, about 10 of them had performance issues or stability issues that we had to look at and investigate further. And one unexpected benefit was we had a previously manual integration task that would take one engineer 8 hours per day, or 8 hours per week, to integrate between our gameplay development code line and our main development code line. And they push one integration in each direction per week. Using our automated system, we were able to increase that to 10 to 20 integrations per day, and with very little actual engineer intervention. We have some stats on the number of builds and tests we've ran so far in our system. And one additional benefit is now we have a permanent pre-flight testing farm available to our engineers to use. And we find that they've been pushing off potential optimizations they want to run overnight. They want to see how effective their change is, and then get that results in the morning. Moving forward, we'd like to move our farm from physical desktop PCs to VMs for stability. Our previous system had a problem with dev kit management, where we were basically assigning one dev kit to one build machine. We're looking at ways to create a resource pooling system for actually allocating and provisioning one dev kit at a time as necessary. We also want to standardize our process so other teams than just the FIFA gameplay team can use this system for their pre-flight testing. First, thank you to our sponsors. And thank you all for listening.